to my next class. Now we'll be looking at enzyme purification and specificity. Enzyme purification is the process of isolating and refining an enzyme from other cellular components. Purification, from the word purification, of course, that is a refining, a kind of processing of the enzyme to make sure that it is clean, to make sure that it is without impurities, So it's enzyme purification, a process of isolating and refining an enzyme from other cellular components. The goal is to produce a high concentration of the enzyme with the highest catalytic activity and purity. Particular enzyme you're looking at for. So when purification is carried out, you see that everything concerning what you now got is that particular enzyme. So it is isolated from the whole cellular components, So the goal is to produce a high concentration of the enzyme with the highest catalytic activity and purity. Now, why is enzyme purification important? It's a question we should ask ourselves. Why would they decide to purify an enzyme? One, purified enzymes are more stable and specific. One of the things about enzymes that make them to be good is specificity. They are specific. Yes. So one of the reasons why it's important to purify an enzyme, because purified enzymes are more stable, active, and specific. Two, they are more efficient and effective in industrial processes. Three, they are used in clinical therapeutics and as diagnostic reagents. Okay, so we'll leave it at that. We'll now come and look at enzyme specificity. What do we mean by enzyme specificity? Enzyme specificity refers to the range of substrates that an enzyme can act on. The range of substrates that an enzyme can act on. Enzymes have different levels of specificity, from highly specific to the ones that are promiscuous. Let's use that word. You don't want to say something is promiscuous. It's not specific. So we have different levels of specificity of an enzyme. So we have the ones that are highly specific. We have the ones that are not that specific. So types of enzyme specificity. We have the one we call absolute specificity. Now, an enzyme that catalyzes a single reaction, just one, with a single substrate. Enzyme that catalyzes a single reaction with a single substrate. Not that a particular substrate is a particular substrate binding to different enzyme, to different active sites of enzyme. No. So a single reaction with a single substrate. We have the one we call group specificity. It means an enzyme that acts on molecules with specific functional groups like amino, phosphate, and methyl groups. So we have enzyme that any methyl group at all they can bind to, any phosphate group they can bind to. We have the linkage specificity. This one, an enzyme that acts on a specific type of chemical bond, regardless of the molecule's structure. Regardless of the molecule structure, as long as that chemical bond that is required is there, the enzyme can bind. The enzyme can act on it, regardless of the molecular structure of whatever. Now, optical specificity, also known as stereospecificity. This is the highest level of specificity. Enzymes are specific to the substrates. They are specific to the substrate's optical configuration or the arrangement of atoms in space. How does specificity work? That should be another question we should ask ourselves. How does specificity work? Now, enzymes are catalysts that increase reaction rates by the lower activation energy. So they increase reaction rate by lowering activation energy. Two, an enzyme specificity comes from its unique three-dimensional structure. Three, the enzyme's active site binds to the substrate, allowing the enzyme to convert the substrate into a product. So that is how enzyme specificity works. So our next class will be on coenzymes. Okay, so you're welcome back to the next class where I said we'll be talking about coenzymes. Coenzymes. So coenzymes are organic molecules that help enzymes. They help enzymes to speed up chemical reactions. Coenzymes are organic molecules that help enzymes speed up chemical reactions. They bind to an enzyme's active site. They bind to an enzyme's active site and can act as electron carriers or functional groups that are transferred between enzymes. So how do they work? Coenzymes bind, like I said, to the enzymes and help them convert starting materials, that is the substrates, help them convert the substrates into final products. Coenzymes can change and often alternate between different forms. They are not specific to a particular enzyme, so they can bind and react with many different enzymes. Examples, we have the coenzyme A, which carries and activates acyl groups in metabolic processes. We have NAD+, nicotinamide adenine dinucleotide, the coenzymatic form of vitamin niacin, which is vitamin B1. We have the flavin adenine dinucleotide, FADH2, a cofactor that controls the enzyme it binds to. We have the PLP, which is the pyridoxal phosphate, the active form of vitamin B6. That is this one I mentioned, the PLP. Pyridoxal phosphate is the active form of vitamin B6, which is involved in many enzymatic reactions. We have the TPP, thiamine pyrophosphate, a derivative of thiamine, vitamin B1, which catalyzes many biochemical reactions. They also have glutathione, a sulfur-containing peptide that is oxidized by molecular oxygen. We have looked at coenzyme. We said coenzyme do what? They help to increase reaction. We said coenzymes, they help to do what? The organic molecule that help enzymes to speed up their what? Chemical reactions. Now we'll be looking at what isoenzymes. Isoenzymes are enzymes that have different amino acid sequences but perform the same chemical reaction. They have different amino acid sequences but perform the same chemical reaction. There are different forms of the same enzyme that are found in different tissues. How do they work? Isoenzymes have different kinetic properties and regulatory mechanisms. They are often organic specific. So they are often organ specific, not organic. They are often organ specific. They allow for fine-tuning of metabolism to meet the needs of a tissue or developmental stage. So we have examples of these isoenzymes. We have the LDH, lactic dehydrogenase, that are found, an isoenzyme that is found in different parts of the body, including the heart, lungs, kidneys, liver, and skeletal muscle. We have the ALP, alkaline phosphatase, an enzyme that can be used to diagnose or monitor bone disease, liver disease, and more. We have the CPK, creatine phosphokinase, an isoenzyme that is commonly used in clinical settings. We have the cytochrome P450 isoenzyme, 1A1. It's also known as CYP1A1. It is an enzyme that is involved in the formation of carcinogens. It's involved in the formation. So when this kind of enzyme is being seen, cytochrome P450 isoenzyme, 1A1, that means it's pointer to something. So it's an enzyme that is involved in the formation of carcinogens. Glucokinase, a variant of hexokinase that is involved in insulin release and glycogen synthesis, is also an isoenzyme. So how are these isoenzymes? How are they identified? That's the next question. How are they identified? Isoenzymes are often identified in clinical laboratories using electrophoresis. Isoenzymes are distinguished. They are distinguished by their electrophoretic mobilities. So the way they move, during electrophoresis, that is how they are being identified. So some are faster than others. So their electrophoretic mobilities are also used to identify isoenzymes. So I think we'll call it a day here until I see us in the class. Make sure you go through these notes very well. Go through it very, very well and digest them and even make your own notes also out of it. God bless you. It's me, Mrs. Omogade, signing out.